Just a little musical interlude there. So, let me continue this sample test. There is, what is the equation of the following polynomials? So given these polynomials, one, I'm going to have a couple of roots here and a y-intercept. So, noticing my roots, I noticed that one of them is x minus 1. The other one is x plus 1. I always do that. Remember, it's a negative root. If it's a negative intercept, it's a positive factor. So this is now x minus 2 and x minus 3. And they are all of order 1, actually, because they all just cross right away, right? And so that's kind of the idea there. Now, unfortunately, I don't know the rest of the function, but I can figure out this little lead coefficient thing by using my x-intercept here. This is point 0, 3, 1, 2, 3. And so what I'm going to do is I'm going to do 3 is equal to a times 0 plus 1, 0 minus 2, 0 minus 3. 0 plus 1 is 1. 0 minus 2 is negative 2. 0 minus 3 is negative 3. The product of this is 6. And so I get 3 is equal to a times 6. Now I divide by 6 on both sides, and it turns out my a value is 1/2. So my actual function is f of x is equal to 1/2 x plus 1, x minus 2, x minus 3. Alright, let's move on to this one here. And I guess let's see here. Oh no, you know what? I totally missed a root right there. Look at that. You see that? I was going to say, I said, you know what we need to do is we need to check to see that I have a third degree polynomial. But I don't. I have a fourth. And so I totally missed a root, and that root is x minus 4. So now I've got a fourth degree, which makes me a negative 4 here, which gives me not, I'm going to carry this down here, 0 minus 4, right there, brings me a negative 4 here, changes this 6 into a 24. That is negative. Now if I divide it over, it's 3 over 24, which is 3 over negative 24, which makes my a value negative 1/8. Okay, and then I'll put in my x minus 4 here, and I'll put in a negative 1/8, and there it is. So I apologize again for the confusion. Hopefully that is a little bit more clear. And that now makes sense. I have a fourth degree polynomial with a negative lead coefficient. Now I've got, it looks like a second order root right there and a first order root right there. Okay, so my second order root is x minus 1. My first order root is 1, 2, 3, 4, 5. I need an a value here as well. So I need some point on the graph. I'm going to have to pick a point. None of these points look really nice, to be honest with you. None of them. I got that one, I got this one. Now when I pick a point, it can't be one of the points I've already used as a root. So you know what I'm going to do is I'm just going to pick that one right there. And I'm going to say that that is negative, or 2 and negative 2 comma negative 1/2. How about that? It's maybe not quite negative 1/2, but we'll just say. So then I've got a negative 1/2 here. Should be equal to 2 minus 1 squared and 2 minus 5. So what I'm saying is when my input variable is 2, my output should be negative 1/2. And so I got 2 minus 1 is 1 squared. 2 minus 5 is a negative 3. And so I got a negative 1/2 over here. Still have my a value, which I forgot to write down. And so I'm going to divide by a negative 3 over here. And so I get a is equal to, dividing by a negative 3 is a negative 1/2, divided by a negative 3 is a 1/6. So my function is f of x is equal to 1/6 x minus 1, x minus 5. That x minus 1 is squared. And is this correct? I have a third degree polynomial with even or positive lead coefficient because the end behavior is like that. Looks good. Nice. All right. There's the everything. Now I'm going to make a rough sketch of the following power functions. Just remember the x to the third power function just kind of goes like that. X to the negative fifth is going to be a little tighter and go like that. So the difference between the third and fifth is that the third is a little wider, whereas the fifth tends to be squished in this way a little bit. I explained that in class. Okay, and moving on, number 10 here. Let's see what we've got. Given the following graph, state the degree of the function and the sign of the lead coefficient. Well, this one's pretty simple. We just got done doing, it looks like it's got 2 turning points, so my degree is probably going to be 3. And that my lead coefficient is going to be negative. Just look at your end behavior chart for that one. Now we're going to do a little bit of average and instantaneous rates of change. So find the average rate of change for the interval 2, 5. Remembering that this is an interval, not a point. This is my function. So essentially we use the difference quotient, or the slope average rate of change. I essentially evaluate this at 2 and 5. And so the average rate of change is essentially f of 5 minus f of 2 over 5 minus 2. F of 5 is 5 squared minus 2, minus f of 2 is 2 squared minus 2 over 5 minus 2. So it's 25 minus 2 minus 4 minus 2. 4 minus 2 is going to be 2, and so minus 4 minus 2, and so now all this is still over 5 minus 2, and I'll just do this. Is 25 minus 2 is 23, minus another 2 is 21 over 5 minus 2 is 3. 21 thirds y's per x. That's the average rate of change over that entire interval. So what I'm saying is over the interval from the x interval from 2 to 5, just sort of using this as sort of like a model from 2 to 5, my average rate of change is 21 y's per every x. That's part A. Part B is essentially the same thing, but remembering to do the instantaneous rate of change, I have to do an interval that's very close to what I'm looking for. And so, given the function x squared minus 2, estimate the instantaneous rate of change at x equals -2. And so, basically what I'm going to choose is I'm going to choose an interval of -2, comma, -2.01. And then that's going to essentially give me a reasonable interval. Okay? Now again, this is just an estimate. So let's basically do the same process, but instead of using 2 and 5, which is up here, I'm going to be using 2 and -2 and -2.1. So I'm doing f of -2.01 minus f of -2 over -2.01 minus a -2. And so f of -2.01 is -2.01 squared minus 2 minus a -2 squared minus 2. Now I know that there's a lot of 2's going on in this place, but you gotta just be careful and try not to make too many errors on this. Now for this, I'm gonna get a calculator. -2.01 squared is probably like, 4.0001 or something. No, 4.04. Minus 2 minus, oh, don't forget, I actually kind of forgot that when you have that negative sign, you're going to have to carry it over. So this is -4 plus 2. I'll write it like this for now. Okay, so this 2 goes there. This is just that. And so basically this minus changes that into a plus and this into a minus. Alright? And then I've got this is 0.01. -2 plus 2 is the -0.01. Let's see. So now what I want to do is just kind of figure out all this here. 4 divided, -2. This is a -4 plus 2. These cancel out, so this becomes a -4. So I've got this -4, which is 0.401 or 0.1. Messed that up. 0.0401 over that. So I'm going to take that, subtract a 4 from it, get that part. Then I'm going to divide by -0.01. -4.01 is my slope, or instantaneous rate of change there. So basically that's just the same idea, but you try and do your best on making sure that we don't have any problems here. Number 12. I'm going to see that my degree is 4 and my lead coefficient is -12. And I'm asking, determine the constant finite differences. Remember, the constant finite differences is C. And so if you remember from the previous page, I've got this formula, a equals c over n factorial. A equals c over n factorial. Now if I do a little bit of algebra here, I find that c is equal to a n factorial. And essentially, I'm just going to take the product of this. And so my constant finite differences is 12 times 4 factorial. 12 times 4 factorial, we know that we do factorials before multiplication. Like, you don't want to multiply this and then apply the factorial. You want to apply the factorial, and then now you would multiply. So it's 12 times 4 times 3 times 2, or 12 times 4 times 3 times 2, oops, 288. And you might get some pretty big numbers there. Okay, now last one, number 13. You'll find that number 12 and 13 I've added onto the video, but they're not on the thing there. Maybe I'll repost this. Is the following function even or odd, and will its graph display symmetry? If so, what type? So I noticed that all of these things are even. Now this one doesn't count so much, but I noticed that these are even, and this basically just takes the graph and shifts it up or down. So even if that wasn't there, it's not going to distort the shape of the graph, and it won't destroy the line or the point symmetry, because all it is a shift. And so basically I'm going to say that this is even, and it's got line symmetry. And then I'll get some points for that. All right, there we have it. And kind of, there you go.